Hi everyone, and welcome to another power electronics class. In the previous class, we did an introduction on different type of conversion. One example was AC to DC. As we know, for AC to DC, we do a rectifier. We use a bridge rectifier. We spoke a little bit about the concepts of switching, uh, different type of conversion like inverters, rectifiers, cyclo conversion, and conversion from DC to DC. We mentioned switching and the importance of switching. Why do we need switching? Switching is needed to convert DC to AC. And we spoke a little bit about pulse width modulation, or PWM. And we did some examples of PWM and how, using the width of the pulse, we can create different levels of DC and AC voltage as well. So if, for example, if we want to, I gave an example of an RC, the RC cars. If we want to determine the voltage and give it a specific voltage, we can change the pulse width, and changing that pulse width, we change the average DC voltage, and therefore we can control the DC motor speed. Today we will continue that, some switching concepts, and also we would continue with the future and the challenges of renewable energy and how it's related to power electronics. And we will finish chapter 1. And next, from the next class, we will start with DC to DC buck boost converters and so on. So the need for switching in power electronics, as I mentioned, it's a big part of power electronics is just switching. I would say 50% of this course is just about learning the switching concepts, different switching equipments. So we will start with that, and the efficiency, some efficiency examples, comparing power supply designs, different power supply designs with different elements like transistors, or if we want to use an op amp, a diode, a tristor, and so on. We would mention what is an ideal switching and what we want the ideal waveform to look like. And we would speak about ideal switch types and also practical switch characteristics. Obviously, if we want to build a switch, we want that switch to be ideal, meaning we want a slew rate which is close to infinite. Do you remember what slew rate was in an op amp? So slew rate is the ratio in which the switch goes from a positive to negative, meaning the slope which we go from on to off. This is our slew rate. And the slew rate, we want it to be close to infinite, meaning we wanted this angle to be close to, the sine of this angle to be close to infinite, the tangent actually to be close to infinite, or we wanted to immediately go from positive to negative and negative to positive, okay? But in reality, when we want to go switch from positive, negative, or on to off, it usually takes some time. And this is our slew rate, okay? And this is an not ideal switch. We have a slew rate. And the lower the slew rate is going to be, we're going to have decrease in power efficiency. So if a switch looks like, let's say this, And you can see, let me make it a little clear. So if we have a switch that looks like this, you're gonna have a lot of waste in the power when we are transitioning from on to off and back to on. Okay. And an ideal switch would actually look like the black one. So we want it to go straight from on directly to off and back to on. But in a transistor, we have limitations, and I'll explain what limitations that we have in a slew rate. And all of these go back to frequency response. If we have an op-amp or a transistor that has a very high bandwidth, frequency response is very high, you're going to have a very fast switch. And if you have a transistor or an op-amp that has a lower bandwidth, you're going to have a slow frequency, lower frequency response and a slower switch. And these are examples of the swing rate, and also they call it the slew rate as well. And for the voltage going from the off to on, and for the current from going off to on as well. Can you tell me why did the voltage and the current go the opposite way when I do on and off? So imagine this is our switch, and we are measuring the voltage here, and we are also measuring the current. What happens to the voltage? Let me draw it bigger here, down here. Let's say we have the switch over here, and I have this, and I want to put the current meter here, and the voltmeter of the switch over here. And I have a source over here. So when the switch is on, let's start with when the switch is off. At this stage, the switch is off. Yes, or it's open. When the switch is off, what is this voltage equal to? It's 0. Let's put it this way, make it a little simpler. Imagine we don't even have this. I'm just measuring the voltage of the switch. When the switch is open, what would this voltage be equal to? I'm sorry? Why? Perfect. So the voltmeter, what is the internal resistance of a voltmeter? It's infinite. So technically it's like an open circuit, yes? For an ideal voltmeter. You learned this in measurements and instrumentation. So if this is an open circuit and this is an open circuit, then this voltage, because these are in parallel, would be equal to the voltage of the source. And by the way, we would assume that the ammeter is also an ideal ammeter, and for an ideal ammeter, Ri for an ideal ammeter is equal to 0. The internal resistance for the voltmeter would be infinite, okay? Therefore, these two are in parallel, they share the same voltage. So V off would be equal to Vs, which is our maximum voltage. Now, what happens if this is on? What would the voltage be for the switch? So if it's V on, then it's a short circuit. And then in short circuit, V of the switch, I'm gonna show it with VSW, voltage of the switch, is gonna be V positive minus V negative. Am I correct? And since they have the same voltage, it's gonna be what? 0 or close to 0, because you have a little bit of internal resistance still, okay? But in an ideal situation, it's gonna be 0. So V on, it's gonna be equal to 0 for the switch. What about the current? What happens to the current? I off. When it's off, what happens to the current? So since this resistance is infinite and this is off and you have an open circuit, there would be no current passing this. So I off, the current would be equal to 0. But when it's on, what is the current going to be? When it's on, this is connected, all the current would directly pass through this. And since we don't have any current, any resistance in the circuit, because we would assume that this is ideal, I on would be equal to I max. In other words, I on would be the current, that maximum current that is coming from the source. Okay. So we have these two and we have these two. Therefore, when the switch is off, we would have the maximum voltage, or Vs. And when the switch is on, it goes to the minimum voltage, or 0, if it's an ideal situation. And for the current of the switch, we will go from 0. When it's off, we go for, maximum. And when it's on, this is IS, or I max. This is when it's on, and this one is off. Again, on, off. Oh, I did the voltage the other way. I'm sorry, let me erase it. So this is, again, this red one, let me do it with a different color. So it's, the red one is our current, and the current when the system is off, it's going to be maximum. This is I off. And when it's on, this is I, what did I do? I on and I off. And for the voltage, when it's off, this is going to be, let me do it with a different color, with green. The voltage, when the switch is off, we're going to have the maximum voltage. And when the switch is on, we're going to have the minimal voltage. So the green one shows the voltage, the red one shows the current. Is it clear? Yes. Do you want me to explain it again, or? So we get this. Now the slew rate is, and the transition time when we turn it on and off, we want this in an ideal situation, this would be square, would be something like this. We would go immediately from maximum voltage to minimal, and maximum, make minimal current to maximum. And the transmission would be immediate. But obviously we have, these switches have physical limitations, and therefore we're going to have a non-ideal situation, which we would have, again, the slew rate that I think you remember from LIC. Now, what type of systems, what type of elements we use for switching? There are different type of elements that we use for switching. Do you remember what this graph was from electronics? This is the voltage current graph for a semiconductor, like a transistor. This is an example for a triode, very similar to a transistor. We had different regions in a transistor. For the VI, we had the saturation region, the cutoff region, and the active region. In the next class, we would speak about different type of power semiconductor devices, such as the power diode, BJT or bipolar junction transistors, power MOSFET, which are metal oxide transistors. We have the IGBTs, SCR, GTO, and GTO and TRIAC transistors, which are the newer generations. We will focus on device current voltage characteristics. We would compare the switching devices like the triodes and triodes, we call it, and also BJT and MOSFET transistors. And we would do a survey of commercially available devices and do some future trends. This graph shows the evolution of power electronic switch technologies. The first devices that came out, first were the bipolar transistors or BJT. They're still in use, and they are new generation for them. They have a lot of benefits. And then we had the SCR. They are actively turned on. They have a firing angle, and I'll explain what a firing angle means. But the problem is they can't be actively turned off, and they are used in higher voltage applications. Then came the power BJTs. Then the newer generation were the MOSFETs, because they are very fast. BJT, the problem is because of the saturation, and the saturation region is pretty large. The switching time is, and the slew rate is actually pretty low. So switching time is pretty slow. You can actively turn them on and off. The voltage is below 300 volts, but the benefit that they have are they are very fast. They were used mainly in like the previous generation of most chargers and inverters. And then came the IGBT, which are again active on and off, but the voltage is higher than MOSFET. It's above 300 volts, below 5,000 volts. They are a hybrid between BJT and MOSFET. And then we have the latest generations, like the GAN or GAN and the SiC. And I'll explain the silicon carbide ones and the gallium oxygen and the newer generation ones. They are wide band gap devices. They are just recently integrated into large applications, especially the advances have made significant progress, made significant advances in the EV field and hybrid vehicles and plug-in hybrids as well. So some figures on merit. What is the objective here in power electronics? Is to be able to produce a converter that performs well in efficiency, transient response, load and line regulations, power density, input-output distortion, or what we call the input power factor, reliability, and cost. Some of these, as I mentioned in the previous class, we have inverters in the range of $50, $60, which are 1 kilowatt inverters. But the problem is they produce square signals. Square signals are good if you want to convert it back to DC, but you can't use it if you want to run a refrigerator or an HVAC system. So these are very cost effective, but their efficiency is low, and the quality of the signal is also low. So you can't have all of them usually together. If it's very efficient, if it's very good at controlling and regulating input output, it would be very expensive. So usually you have to compromise and pick between one of these that you want. So again, if it's usually cheap, it's not efficient, the efficiency is low, the quality of the signal is low, the control system in it is not sophisticated, very simple. The power density is not that good. So you have to compromise. The reliability is also low. So if you want to build a grid connected inverter, by the way, grid connected inverters are the highest quality usually, because you have to be able to match the grid frequency in real time, match the grid voltage in real time, and match the power factor, everything, and be able to cut the power if you need a power. So it's a unidirectional system sometimes, and sometimes you need a bidirectional system to be able to get power from the grid and give power back to the grid. I'll give you one example. Imagine if you have a solar panel, a PV, photovoltaic panel, and you connect that PV photovoltaic panel to an inverter. I'm just going to call it a DC to AC inverter, okay? Now, if I want to use this at home for a home application, it's pretty straightforward. Imagine I have a 400 volt system. The only thing that I need to do is to convert DC to AC and the voltage to 120 volts, 60 hertz. Okay. But if I want to connect this to the grid, imagine I have a grid, sorry for the bad drawing, and I want to connect this to the grid. Now I have another problem. Okay. If I want to provide voltage to the grid, I must have a higher voltage than a grid. What happens if I have a lower voltage than a grid? I'm going to get the power. Okay. So you need a little bit of higher voltage. And also you need to match the frequency. Okay. So if you're producing a 50 hertz frequency, okay, you cannot connect a 50 hertz to a 60 hertz. It's going to damage your equipment or even the grid's equipment. It's going to be very, very dangerous. So you need to match the voltage and you need to match the frequency. What else do you need to match? Do you think? Imagine you have a generator, like a gas generator. You want to generate power and you want to sell it back to the power company. Okay. How can I even match my generator to the grid? What should I consider? So one thing is voltage. Obviously, we want to match the voltages. If their voltage is higher, it's like you having two tanks of water. Their tank is higher than your tank of water. The water is going to flow from their tank to your tank. If your voltage is higher than their voltage, your tank is going to water flow to their tank. Okay, that's the electrical potential as well. Next thing is frequency. Obviously, if we had DC connected to DC, we won't have this problem. But since it's AC, we can't connect to 60 hertz to 50 hertz. So imagine you run your generator or your inverter. It's generating 120 volts at 60 hertz. Can I go and just connect it to the grid? Why? Another bit factor, and this is one of the most complicated, matching the voltage and the frequency is the easy part. The difficult part, imagine this is the voltage and the frequency of your grid, and the green one is what you're producing. You're producing 60 hertz, but it has a phase shift of, let's say, 2 degrees. This, again, is going to create huge problems because when your voltage is at 0 volts, the grid voltage is like 50 volts or something like that. You're going to have a mismatch. So the next thing is we need to match the phase as well, okay? And we use a thing called a synchronizer. I don't know, have you seen them if you've been to a power plant, these big, like, there's a big dial that shows when the frequency of the system matches the frequency of the power plant matches the frequency of the grid. And you have to perfectly match that. If it's a little bit of alternation, like 2-3 degrees, it's going to damage both the power plant, and that's a 300 megawatt power plant, and also the grid. Going to create a lot of problems. Now, how do we do that? How do we match two frequencies? Imagine you have two cars, both of them are going at the same speed of 60 miles per hour, but one is 1 mile behind the other one. How do we match them? So the way that we want to match them, again, imagine we have two objects. They're going the same speed. Let's say they are going 20. It's 20 is too low. Like, let's say they are going 100 miles per hour. Okay. 100 miles per hour. And we want to match them. But the problem is one of them is like one car behind the other one, or two cars behind the distance of two cars behind the other one. And this is exactly what happened. Imagine you have a semi truck going 100 miles per hour, and that's your power plant. And you want to connect the trailer to it. So first thing you have to do, you have to match the speeds and you have to align them perfectly so they would connect together. And this is the difficulty of a power grid. You have to be able to match their speed and their voltage. Okay, now how can I do that? The one that is behind should go a little bit faster, okay? So what we do is we increase the frequency of the power in the first one, so it will match the second one. But we have to do it very careful because if this goes very fast, it's going to fall ahead of the second one. So you have to do it very, like the frequency goes from 60, 61, 62, 63, then goes back to 62. So you would actually make one a little bit faster until it, reaches the second one, and then you would. So if it's like this, you're going to have something that goes like this. So imagine the green one is like this. You're going first like this, then you would slow it down until it matches the second one, okay? So you change the frequency. So how do we change the frequency in a power plant? The good thing is we have a miniature power plant in our lab downstairs. If you want, I can show it to you. It would show you a great example of how we do that. But how we do it in a power plant is we control the input valves and we control the amount of steam or gas exhaust that goes into the turbine, and by actually controlling the gas speed flow, we can control the turbine speed and the generator speed, and we can control the frequency. Now, in a power electronic system, we don't have any moving parts like a generator. It's completely different. We do that through a control system. We have a feedback system that goes back, and we actually get a sample from the grid. We give it back to the inverter, and that actually gets a sample from the frequency of the grid and measures the frequency, the voltage, and also the phase, and matches that to the grid. Okay, so continuing of the objectives of our systems, we can have efficiencies approaching 100%. We use switches in saturation mode on and off. on state resistance can be down in 10th of ohms. Again, if we want efficiency to go up, the speed to go up, we need to spend more. It's going to be significantly more expensive. The inverters that you may need for converting DC and connect it to a grid for 5 kilowatt is around 2,000, something like that. It's more expensive actually than the photovoltaic system itself. Nowadays, because of the newer materials that we use in our transistors and advancement in transistors, they are much smaller compared to the older generations. They have higher switch frequency response and higher switching frequency. That means they have smaller magnetic components and they have reduced losses. When you have reduced losses, you generate less heat, and therefore you would have smaller packaging as well. And these are some barriers to scalable PV storage systems currently that we have. These are the reasons that PV plus battery systems have not taken off yet. We have solar systems that are grid connected, but they usually don't have a battery package connected to them because the battery component is very expensive. Therefore, the revenue model are not clear. And we need accomplishment in power electronics and especially in battery technology to be able to make them cost efficient. They have complex installation, maintenance, and expensive value chain. We have the PV generation and load profile mismatch. As mentioned before, the dot curve, we generate solar mostly in afternoon, which we don't use them, and there is a big mismatch between the load and the generation. We have PV intermittency. We have battery operation at high ambient temperature. As you know, when the temperature goes down, the battery storage also goes down. The batteries don't perform at low and very high temperatures. And at high temperatures, actually, they degrade much faster. That's the reason they ask not to charge your phone when it's, getting very hot. It's going to degrade the battery much faster. Usually the recommendation is if you have a cover that keeps the heat inside, it's better to take the cover off if you want the battery to last longer. And you may ask, and that's a question that I had before, why do a battery in an EV last much longer than a battery in a phone? They have almost the same chemicals, same structure, but an EV battery lasts 10, 15 years. Now they have warranties for 150,000 miles on them, 10 years, 15 years. Better than a battery on a smartphone, maximum would last 3-4 years, and it would degrade. The degradation is much faster compared to EVs. Do you know why that is? Why we were able to manage to get more life out of an EV battery? I'm sorry? Yes, perfect. Yes. The EV batteries, they have a dedicated cooling system. So you usually have a liquid running between those batteries, and you have a radiator that cools the batteries. If you had an EV and if you charge it, you would hear the fan running, especially when you connect it to a supercharger, and it's actively cooling the battery. So it has an active cooling system, and it has a very sophisticated BMS. BMS is a battery management system, which controls the flow of the charge and discharge. It doesn't allow the battery to charge very fast or discharge very fast. And usually it doesn't allow the battery to completely deplete. If you completely deplete the battery, it's going to damage the battery. And because we have this cooling system, I'm going to draw it with red. So imagine you have a pipe running through your battery cells, and you have a radiator to cool it down, this battery is gonna last much longer. The ideal situation for a battery always is to charge it between 20 and 80%. If you want the battery to last longer, never let it go below 20 or above 80%. And the charging cycle is usually 500. Newer generation is 1,000 charge cycles. So from 0 to 100, if it's 1,000 times, it's going to degrade the battery to about less than 80%, and then, or sometimes the threshold is 70%, and then it's the time to change the battery, and that's the expensive part. But the good thing is 70% is not good for an EV, but it's still good for a grid connected system. So nowadays what they do is actually when a Tesla, for example, gets towards the end of its life and the maintenance cost is too high, the most expensive part is still the battery. They take out the batteries, like a few $1,000s worth of battery, and then they would connect it to the grid and they use it as a backup for the grid. So you may not be, viable, useful for a car, but still it has 10, 15, 20 years left in it if you want to use it in a grid. Because we don't care about the weight of a battery in a grid, we care about the costs. So that has become a huge market right now. They are using salvage batteries from these EVs. They are simply connecting them to a grid with an inverter. They buy power from the grid during the midnights, during the day, and then selling back to the grid at a higher price. Now, I'm going to speak a little bit about the energy access challenge and why the power electronic plays a key role in this, and also introduce you to a little bit about IEEE. How many of you are part of IEEE? So I would highly recommend that you become a part of the IEEE community. It's going to open a lot of opportunities for you, especially in the job market. And also, the other thing that is very important, actually, it's going to make your resume much stronger if you're part of the IEEE, community. And they have, I think, regular meetings every other month in the department. I don't know who's the chair right now for the IEEE, the student chapter. I think you can see it in the board. But again, I would highly recommend that you become a part of the IEEE, the community. It's one of the largest engineering, communities out there. And it would help you doing research, finding jobs. Becoming a student member is a very prestigious thing to do, and so I would highly recommend it. So what problems that we have right now is energy access. Around more than 700 million people don't still have access to energy, and around 3 billion live with extreme energy poverty. And energy poverty means that they have access to less than 200 watts an hour per day. So they would have access to 200 watts just for 1 hour a day. And 200 watts is barely enough to keep the lights on. And 3 billion people live in energy poverty. And the problems that we have right now cannot be solved with the 20th century solutions. We have in most first world countries. In first world countries, we have a centralized system, these big power plants, and we have long transmission lines. They are very expensive to develop in the first place and very expensive to maintain. And the problem is with these third world countries and developing countries is that they don't have the infrastructure to do that. I'll give you an example. In Saharan African countries, instead of them building these, a lot of these countries, instead of building telephone like landlines, they go straight to cell phones and wireless communication. Okay, because it's going to be cheaper. You don't need to dig the ground and lay a copper line or a fiber optic. You can straight go to wireless, and we can do that for renewable energy as well and energy as well. We can just skip these big coal and gas power plants and directly go to renewable energy. Just install solar panels for rural areas, and but the problem is, again, the cost is coming down, but we need other things rather than cost, like expertise and people to install them. These are some examples of the existing approaches, but so they are happening a lot. You can see that they are using them, solar energy, for clinics, for pumping water. They are using it in industry, for transportation. This is a good example of grain milling transformation, using just their hands to do it. Takes a lot of time and effort. Then they switch to a gas power system, and now most of them are converting to a solar powered milling system. So we have different challenges with existing approaches. First challenge that we have is these systems, the power systems that we have, are centralized. They're high cost, high maintenance, long implementation cycles. It takes few years to a decade to build a power plant. It requires skilled labor to install and operate. They're inflexible. They require on fossil fuels. They depend on fossil fuels, and they need non-existing baseload. The distributed system, it's the top-down microgrids and SHS systems are too expensive and customized, and they cannot start small and expand as needed. Where need for future integration with the grid poses a challenge, so top-to-down microgrid is not a solution as well. The best systems that we can have right now for these type of communities is to have independent individual solar systems. So sometimes some governments subsidize, and people would just install the PV panels on the rooftop. They can even be trained to install them themselves. So they doesn't require a lot of expertise to do that as well. So loads served in these situations are significant. There have been significant progress in solar lights and phone charging, but there are still some challenges with high cost of energy in these situations, and how to be able to improve it. And the other problem, the main problem actually, is that having the system that works reliably in an off-grid situation, and we have a very reliable off-grid battery storage system. So then that's when IEEE comes into picture. We have a program called the IEEE Empower a Billion Lives, and there are a lot of Congress, there are a lot of seminars and that they hold every year for advancement in technology and making these systems available. They have some global competitions with global prizes. And I think last year, 2 years ago, I attended one of these. It was very, very, very interesting, and you meet a lot of interesting people. You expand your network, and learn a lot of new things, the cutting edge technologies out there, and if you have a good idea, a conference paper, um, you can submit it and probably win an award as well. If someone is interested in doing research with me, just you can contact me. I'll have a lot of projects going on. I can support you if you want to go to a conference as well. Just let me know, send me an email, and we can start from there. I just wanted to mention this as well. And these, again, the access challenge that we have, these are, this actually shows, you know, different situations and how we can utilize the regional power. One way to do that is to use, local supply and local labor to be able to build these devices. Obviously, building a solar panel is a little bit more challenging, but building the structure for the solar panels, the switches, some even wiring and connections and connectors and things like that could be done locally. So you would create jobs and you don't need to transport the equipment to the site, and it's going to be much cheaper, much faster as well. These are some prizes. The 2023 first prize was a nanogrid in Madagascar, and you can see other projects as well. One is a solar freezer. One is just using organic waste. Using that organic waste, you could generate energy by generating methane, and then you can store that methane in biotanks and later use it for later use. So you can just, have a few tanks, store the methane, generate power whenever you need it. This is another standard microgrid. You see the solar panels on top of the container. The container is when you put the batteries and inverters and all the switches and so on. And again, different appliances, different applications for solar energy, and that actually were submitted to that conference. So some technology needs and leapfrog innovations and innovation opportunities. There could be a lot of progress done in the affordability, supply demand match, and productive energy use, scalability, and sustainability. These are the higher level needs, and the technology opportunities are the bottom up grid solutions, ultra high efficiency appliances. The switch from regular lamp to these LEDs, the fluorescence and then the LEDs has actually made a huge difference, because normal lamps, they consume like 100 watts, creates 50 lumens. Now you can create the same amount of light from a 60-watt lamp with a 5-watt lamp. So they cut it 10 times the power requirement, and it's going to last 10 times more. And nowadays it's become much cheaper as well. Energy access solutions, monitoring and data. AI is playing a big role here, especially in microgrids. Reducing e-waste, extending lifetime of batteries, increasing system reliability, and also automated plug-and-play operations as well. And this is the website for Empowering a Billion Lives. If you're interested, there are a lot of conferences. If you're interested, Let me know if you have an idea that you'd like to work on. I can help you. I also have some research topics that we can work on. One example is, I think last 2 years ago, there was a water initiative. One part of that is actually they are working on sustainable and energy efficiency on water desalination, and the prices, I think for the first place is 100,000, the second place is 50,000, something like that. So there are a lot of opportunities out there for doing research and yeah, changing lives probably. Thank you so much. That's it for today. We are finished with the first chapter. I'm gonna start with the second chapter on Wednesday. And that is gonna be buck boost converters, DC converters. Thank you.